Okay, so today we are talking about how to solve problems using lines. Up until this point, we've talked about how to create the vector equation of a line, and now we're going to use those lines. So let's say we have two lines here, and they are asking us in this first example to find the angle between them. Now we've talked about how to find the angle between two vectors, and that formula is on our formula sheet, and it looks like this. The dot product of vector A and B over the magnitude of vector A times the magnitude of vector B. But we need to decide which vectors we are going to use in order to plug into this equation. So what vectors are we finding the angle between? Well, really, as long as we are using vectors that are representing the direction of this line and the direction of this line, we're going to find the correct angle. Which vectors are the vectors that are talking about direction? That's always this attached to our variable right here and right here. Those are our direction vectors. So if we're trying to find the angle between two lines, we want to be talking about those two. So from there, it's just a matter of plugging into our equation. So we have cosine. Oh, I have a highlighter there. Okay, so we have cosine of theta equals the dot product of 1, -1, 3, and -1, 4, 1, all divided by the magnitude of vector A, so that's 1 squared plus -1 squared plus 3 squared, times the magnitude of vector B, which is -1 squared, 4 squared, and 1 squared. Okay, so from there, we're just cranking it out. Let's see. We have 1 times -1 is -1, -1 times 4 is -4, 3 times 1 is 3, and then in the bottom we have the square root of 1 plus 1 plus 9 times the square root of 1 plus 16 plus 1. So that gives us, let's see, -2 over the square root of 11 times the square root of 18, and that's equal to cosine of theta. And so we should be able to solve from here. So we are going to take cosine inverse of both sides. And when we do that and use our graphing calculators, that gives us that theta must be 98.1713 ... degrees. Now, thinking back to the original question, it said find the acute angle. So thinking about our two lines, when we were talking about this, if 98 degrees we know is not acute, so that's got to be the bigger of the two angles right here. So if this is 98 degrees, then this would have to total 180 with it. So we can do 180 minus the 98.1713. And that gives us 81.8. And that is an acute angle. Because really, when we're talking about the angle between two lines, we have both angles. We have this angle right here and this angle right here. They're both the angle between the two lines, but one is obtuse and one is acute. So we need to make sure we found the acute one. So here's our key point. Whenever we're trying to find the angle between two lines, we're finding the angle between their direction vectors. And once we do that, we can just use our formula that we know for finding the angle between two vectors. So another example of what we were just talking about asks us to decide whether the following lines are parallel, perpendicular, or neither. And so really it's testing whether we know which vectors to use, because as long as we know which vectors to use, we're just plugging into the formula. So for part A, the two vectors that we are going to use is this one and this one. And we plug right into this formula. Dot product of our two vectors divided by the magnitude of our vectors. 4 squared is 16, -1 squared is 1, 2 squared is 4, 1 squared is 1, 2 squared is 4, 3 squared is 9. And when we do that, we get 4 plus 2 minus 6. Now, I'm going to actually stop right there. 4 plus 2 minus 6 gives us 0. So if the dot product between two of our vectors is 0, then the whole thing is going to be 0. We know that that means that they are perpendicular. So for part A, our answer is that they are perpendicular. Okay, try B and C on your own, and I am going to work them on my own, and I'll put up the answers in a second. So go ahead and pause your screen and work B and C. Okay, so here's what I got. For part B, we get that the angle between them is 97.4, so that means that they're not perpendicular or parallel. For part C, when we calculate it out, we get that theta is 180 degrees. Well, for the angle to be 180 degrees between one line, 180 degrees would then make the other line right there. Well, that really means that they are going the exact same direction, so they are parallel. Okay, so the next thing that we're going to talk about, besides finding the angle between two lines, is talking about finding the intersection between two lines. Now, especially, we're going to be talking a lot about lines that are in 3 dimensions. And so this opens up a lot of different options for us. Before, when we used to talk about intersections of two lines, the only options were they could intersect or they could be parallel and not intersect. But now that we have 3 dimensions, there are more options. They could still be parallel. That would mean that they would have to be on the same plane and parallel, going the same exact direction. The other option is that they could be skew. They might not be parallel, but they still could. That doesn't mean that they intersect. So that if I were to draw a picture, it'd be hard to draw. But we'd think about one line being here, let's say, and then come 5 feet towards yourself off the screen, and another line is coming like this. Well, they're on different planes, so they're not going to intersect, okay? So that's skew lines. Coincident is just a fancy word to say that they are the same line. They share a point, and their direction vectors are the same, or scalar multiples of each other. Or they could just flat out intersect. So then they have exactly one point that is in common. So go ahead and pause your screen and write down this information, and then go ahead and unpause, and we'll go to the next slide. So here are your steps to calculate the intersection point of two lines. You are going to set the components x, y, and z equal to each other. So that means that we are going to take our equations of our lines and we're going to condense them into a singular vector, and then we set the x component on one line equal to the x component of the other. Take the y component of one line, set it equal to the y component of the other, and the z, and set those equal to each other. When you do that, you basically have a system of equations. You have 3 equations, but you only have 2 unknowns. So you can choose which 2 equations that you want to use to solve your system. However, since you only have 2 equations that you're using to solve the system, what can happen is that you get something that works for those 2 equations but doesn't work for the third. So the third step always needs to be that you plug in your scalars, what you just solved for, to both your equations to find out your point. If you get the same thing from each line, then they do intersect. But if you get different things for each line, then they don't intersect, and that means that they must be either parallel or skew. Now, a lot of times IB will say calculate the intersection point of the following 2 lines. If they say that, they are telling you that there is an intersection point, so you don't have to worry so much about the trickiness of them not intersecting. But if they phrase a question in the way of find any intersections between the following lines, then you might come up with an answer that says there is none. They don't intersect because they are skew or because they are parallel. So we're going to look at some examples. Okay, so here's our first example for finding the intersection of these 2 lines. And the first thing that we're going to do for both of our lines is we are going to write them each as a single vector. Here's my first one. And I'm just going to go ahead and say 0 plus 1t, negative 4 plus 2t, 1 plus 1t. I just went ahead and condensed that. Same thing for our second line. 1 plus 4s, 3 minus 2s, 5 minus 2s. Okay, so we've taken both of our lines and we've written them as a single vector. This allows us to look at the components individually, the x component, the y component, the z component. Now, if you have two different lines, you're typically going to be using two different scalars or two different variables, which is what we see right here. This one's t, this one's s. Okay, so what we are going to do is we're going to set up our system of equations by taking our x component of our first line, which is 0 plus 1t, or just t, and I have my highlighter going again. Okay, there we go, t, and set it equal to the x component of our second equation, which is 1 plus 4s. We're going to then set our y component, negative 4 plus 2t, equal to our y component of our other line, 3 minus 2s. And then we're going to take our last one, which is 1 plus 1t, and set it equal to our other z component, which was 5 minus 2s. Okay, so now we have a system of equations. We have three equations. We can use any method that we want to solve. Substitution is looking like a good one because we have just t by itself right there. Or elimination is looking like a good one because here we have negative 2s and negative 2s, and if we just make one of those all multiplied by negative 1, the s's will cancel. So it really doesn't matter which way you want to go. Like I said, just pick one, whichever your preference is. A lot of times elimination is a good option for us with these, but really it's up to you. So I'm going to go ahead and use elimination. I'm going to take this equation, I'm going to multiply it by negative 1. So now it's going to become 4 minus 2t equals negative 3 plus 2s. And I'm going to take this equation straight over. 1 plus t equals 5 minus 2s. The reason I did that is because now when I add going down, those are going to cancel. We get 2, negative t, and 5 right there. Now, continuing on, we subtract 5 from both sides. We get negative 3, so we get t must be 3. Okay, now that we know that t must be 3, we might go back to this one just because t's nice and isolated right over there, nice and easy spot, and plug in t equals 3. You could plug it into any of the equations you wanted. It really wouldn't matter which one. Okay, so if I do this, I subtract 1 from each side. I get 2 equals 4s. So that means s equals 2/4, which is 1/2. So I solved for our scalars right here. We have s and we have t. Now, the reason we did that is because we want to plug in and find the point that they intersect. So what this says is that the R1 equation is going to intersect with the R2 equation when t is 3 or when s is 1/2. So since it says find the coordinates of the point of intersection, I really could assume that there must be an intersection because they phrased the question this way, but I'm going to show you the whole process just so that we're clear on the whole thing. So what I would do is I would take 1/2 for s and I would plug that in to my R2 equation. So I would take R2 equals 1 plus 4 times s, or 1/2, 3 minus 2 times 1/2, 5 minus 2 times 1/2. That's R1. And I'm going to take my t equals 3 and I'm going to plug it into my R1 equation. So 0 plus 1 times 3, negative 4 plus 2 times 3, 1 plus 1 times 3. And there's my other. Now I'm going to simplify each of those, so that gives us 3, negative 4 plus 6 is 2, 1 plus 3 is 4. That gives us the coordinates of our point. And I'm going to do it on the other side as well. So 1 plus 4 times 1/2, that's 1 plus 2 is 3. 3 minus 1 is 2. 5 minus 1 is 4. Okay, now, did we find the coordinates of the point of intersection? We did. We know that there is a time when our first line equals 3, 2, 4, as well as a time when our second line equals 3, 2, 4, and that happens all at once. So that means that we have found the coordinates, and it's important that we write it as coordinates. So 3, 2, 4 is our point of intersection. Now, what would happen if these lines didn't in fact intersect? What would happen is we would have gone back to this step. We would have solved this whole thing. We would have gotten a scalar for t and a scalar for s. But what would have happened is when we went to plug it into R2 and we went to plug it into R1, we would have ended up with different vectors. And that would have been our clue that, oh, these two lines don't intersect because we got that this point is different than this point. And that would be how we would know that two lines didn't intersect. If I was wondering if they didn't intersect because they were parallel versus if they were skew, parallel is easy to spot, right? Our direction vectors would have to be scalar multiples. If they didn't intersect because they were skew, then they wouldn't be parallel. So that's the way to go right there. So that's your process. Set your components equal to each other so that you get a system of equations, solve for your scalars, plug in your scalars, and check to make sure that what you get for one is the same as what you got for the other. Okay, I want you guys to give this one a try on your own. So go ahead and pause the screen. I'm going to work it out as well, and unpause when you're ready to check your answer. Okay, so once you've found your values for t and s and you have plugged them in for R1 and R2, you find that it gives you two different points, which means that despite the fact that we solved for an s and a t, it does not work. The lines must not intersect. Looking at the direction vectors, 1, 1, 4, and 2, negative 3, 2, they are not scalar multiples, so these lines must be skew. They don't intersect. Now, this problem came from your textbook, and if IB had given this to you on the actual test, it's my opinion that they would not have phrased it, find the coordinates of the point of intersection, because it's kind of sneaky because there's not an intersection. So I think they would have phrased it a little bit more a little differently to leave it more open to interpretation. Now, one thing to be very careful about, you might have solved this problem, you might have done all the right steps and gotten different S's and T's than I did. And the reason for that is because if you chose two different lines, so for example, I used the first one and the second one to solve for my t. And then the first and the third to solve for my t. And then I used my second to then solve for my s. So that's the t and the s that I got. But let's say you used equation 1 and 2 to solve for your t and then plugged that in for your third equation to get your s. Your t and your s will likely be different than mine, and that's okay. It doesn't mean you did anything wrong. So that does make it a little bit more difficult to check your work with a neighbor or a friend, because as you work these problems, if you don't choose the exact same two equations to use to solve your system, you will have a hard time comparing what your scalars are or checking your work from there, because you will get different answers. In the end, you should still get, if there is an equation, if there is an intersection between the two lines, you should still get the final points the exact same if there's an intersection. But your scalars will be different. So just keep that in mind. Okay, so this is a question from your textbook, and it requires some heavy algebra. So we are definitely going to set it up together and talk about it. So it works very similarly to a problem we did the other day in class. So it gives us the equation of a line, it gives us the coordinates of point A, and they want us to find the coordinates of point B. And we want to show that we want to find the coordinates of point B so that AB is perpendicular to the line L. So we're starting out by saying, well, we want AB, whatever that vector is, to be perpendicular to line L. Well, that means it has to be perpendicular to the direction vector from line L, and the direction vector is this one. So we know that they are perpendicular. That also means, if they're perpendicular, that the dot products between them will have to be 0. So that's important to keep in mind too. Now, in order to find the vector AB, we would take the position vector B minus the position vector A, which we know is 3, 9, negative 2. So that would give us vector AB. Now we don't know position vector B because we don't know the point B, so that's what we're trying to find. We do know that point B must be on the line. We know it's on the line because it says find the coordinates of point B on L, which is the line that they gave us. So if it's on the line, we know that it has to be in the form of 3 plus 1 lambda, negative 1 minus 1 lambda, and 0 plus 1 lambda. So position vector B has to look like that because it's on the line. We know position vector A. Now what we can do is we can condense those two vectors. So that would give us, 3 plus lambda minus 3 is just lambda. Negative 1 minus lambda minus 9 is negative 10 minus lambda. And lambda minus negative 2 is going to give us lambda plus 2. So that is our vector AB. Now we know, because we just said it above, that this vector has to be perpendicular to 1, negative 1, 0, which means that the dot products have to equal 0. So for part A, all we're going to have to do is say that this vector AB, let's see, there we go. This vector AB, which is lambda, negative 10 minus lambda, lambda plus 2, dot product with 1, negative 1, 1 has to equal 0. So that's just some algebra for us to work out. Okay, so I went ahead and finished solving for lambda. That does not quite solve our question. The question says find the coordinates of point B, and we found lambda, which helps us, but we're not done yet. We said that the coordinates of point B were this right here, which came from the original equation of the line. So in order to find point B, all we have to do is plug lambda in to that right there. So that means that B is going to be 3 plus negative 4, negative 1 minus negative 4, and then just negative 4 itself. So that tells us that point B has to be negative 1 plus 4 is 3, and then negative 4. So our coordinates for point B are negative 1, 3, negative 4. So that was our part A of the question. Part B of the question says, hence find the shortest distance from A to L. Now, they used the word hence, which means that we are definitely going to use what we just did for part A to help us with part B. We know that the shortest distance, if we have, let's say we have a line that looks like this. Okay, here's our line. And then we have some point here. Well, what's going to be the shortest distance from this point to this line? Is it going to be this distance right here or this distance right here? No, it's not. It's going to be the distance where that point is perpendicular exactly to that line. That's going to be the shortest distance. So we already found the point B so that they would be perpendicular, this AB right here, to this line L. So we already found that point. So we just want to find this distance from A to B. Well, what is distance between 2 points? It's the magnitude of vector AB. So to do part B, all we have to do is find the magnitude of vector AB. So we know vector B. Let's see, we have it over there. We know vector A, so AB is just going to be vector B minus vector A, and vector A was 3, 9, negative 2. So negative 1 minus 3 is negative 4, 3 minus 9 is negative 6, negative 4 plus 2 is negative 2. So that is our vector AB. And to find the distance from A to B, all we have to do is find the magnitude AB. And we know how to do that. So the magnitude is going to be the square root of -4 squared plus -6 squared plus -2 squared. So that's 16 plus 36 plus 4. Oh, I am just trying to scroll and let's see. Okay, and so that gives us 56. Let's see. The square root of 56. That is our distance from A to B, or the shortest distance from point A to line L. It is not uncommon for IB to give you a question asking you to find the distance between a point and a line. It's a lengthy process. I wouldn't say it's common, but I wouldn't say it's uncommon either. I've definitely seen it show up. So the way that you do that is you have to find what point will make it perpendicular, like we did in part A, and then you have to figure out the magnitude of that vector AB. Okay, so we have touched on this real-world application, but now that we know our processes for writing the equation of a vector line, for finding the angle between vector lines, for finding the intersection between vector lines, we can finally start talking about some of the real-world applications because we know how to work with these lines. So one of the most common real-world applications is talking about the movement of an object. And we could be talking about any object. We could talk about planes, cars. A lot of times the problems talk about hot air balloons. I mean, it really could be anything. The projectile of a ball moving through the air, anything. The idea is that when we are talking about the movement of the object, we're talking about movement over time. Well, movement over time, distance over time, is velocity. So the key is that not only does this vector tell us direction, but it can also tell us velocity. Now, there is a very important difference between velocity and speed. Velocity is going to be that vector right there. It's telling you what distance you are going in each direction. So direction is a key part of velocity. Velocity is not just a number. It's telling you the direction that you're moving. Speed is your total distance over time. So let's just think about this. Remember that vectors, if I had this vector 2, -3, that would say that I was going in the direction of 2 to my right and -3 down. That means that my vector would probably look like that. Okay, well, how my velocity vector might be that I go 2 to the right and -3 down over the course of 1 minute or 1 second or 1 hour or whatever. But my speed is this amount of time, this amount of distance over my time, because that is the distance I actually went. I didn't actually travel 2 to the right and 3 down. I just traveled in that direction. So my path went right here. So now my whole screen looks like a mess. But speed is your total distance over your time, whereas your velocity is talking specifically about your distance with your direction. So in order to calculate speed, you're just going to calculate the magnitude of your velocity vector. Okay, so in this example, it tells us the direction that we are traveling. We're traveling 5 to the right, let's say, for every 2 that we're going down. Let's just say that that's what that is saying. Okay, so, but it's giving me that we are traveling at 4 kilometers per hour. So this right here, 4 kilometers per hour, that's our speed. We all have talked about our speed before: driving a car, driving a plane, not driving a plane, flying a plane, and so on. So that's our speed. Here's our direction. We're trying to find our velocity. Our velocity is going to be a vector that has the two components, x and y, and it's going to represent the fact that the speed is 4 kilometers per hour and that the direction is 5, -2. So what we are looking for is a vector that is parallel to this, has this exact same direction, but has a magnitude of 4, because our speed is always our magnitude of our velocity vector. So we've done problems like this before where we are trying to take a vector, 5, -2, and scale it longer or shorter based on the magnitude we desire. So the key for that is to go ahead and find a unit vector. And our unit vector is going to be 1 over the magnitude of 5, negative 2. So 5 squared plus negative 2 squared times our current vector, 5, negative 2. So that is 1 over the square root of 25 plus 4, so this 1 over the square root of 29. So our unit vector is 5 over square root of 29, negative 2 over square root of 29. So this is a vector that is parallel to the direction we're going, 5, negative 2, but is only going 1 kilometer per hour right now. Because it is a unit vector, it has a magnitude of 1. We want our velocity vector to have a speed of 4 kilometers per hour. So we're going to take this unit vector and we are going to multiply it by 4. So our velocity vector will now be 4 times that 5 over square root of 29 times 2 over square root of 29. So our velocity vector is 20 over square root of 29 and negative 8 over square root of 29. Now, if I were being really good, I would take those radicals out of the denominator, but I'm going to go ahead and skip that step for today so that this video doesn't get too long. So this process is the exact process that you will always use if you're trying to find a velocity vector and you have a direction vector and you have a speed. You're basically just taking that direction vector, 5, negative 2, and you're trying to scale it up or down to the magnitude that they give you for the speed, and that will give us our velocity vector. So what this would interpret to say is that we are going to the right 20 over square root 29 per hour and down 8 over square root 29 per hour, and that's how far we're traveling per hour. This is our velocity vector, this is our speed. Okay, so I want you guys to give this one a try on your own. They have given us the speed, they have given us the direction. Find the velocity vector, just like we did on the last problem. Go ahead and pause your screen and unpause when you're ready to check your answer. Okay, so here is our final answer. Excuse the messy handwriting, but velocity would have to be 250 13ths, 0, and negative 600 13ths. Start by finding the magnitude of our direction vector, use it to find our unit vector, and then scale that unit vector up so that the magnitude of our velocity vector is 50. That tells us that this is our velocity vector with this speed and this direction. Okay, so we have talked about a lot of skills for today with the equations for vector lines. I want you to practice by doing your homework 11G, questions 1A, 3, and then 8A, B, C, and D. And go ahead and work on it now. Let me know if you have questions, and we'll talk about it more in class.